Hello, welcome to Maths with EJD. In this video, I'll be talking about properties of eigenvalues under matrices. Properties of eigenvalues. And the outline for this video will be like this: introduction, the properties of eigenvalues, and then we'll talk about a conclusion. And of course, as usual, you have some practice questions. So the objective of this video is to understand the properties of eigenvalues and their importance in linear algebra. That is, you understand the properties of eigenvalues and how you can actually, you know, do some things with some matrices without actually going through some stress. Okay. All right. So let's start. Let's take the first property. The first property relates with the idea of transpose. And it says that a square matrix and its transpose have the same eigenvalues. So a square matrix and its transpose have the same eigenvalues. So if you consider the matrix A now, which is 4, 1, 2, 3, its eigenvalues are lambda 1 equals 5 and lambda 2 equals 2. Of course, if you are wondering, maybe if you've forgotten how we find eigenvalues, generally speaking, we look for the determinant of A minus lambda I, equals 0. That's how we find eigenvalue. So in that case, it means matrix A is 4, 1, 2, 3, right? A minus lambda I would simply be, of course, you are looking for now the determinant of 4 minus lambda 1, 2, 3 minus lambda, and all of this is equal to 0. So this is 4 here. So if you take the determinant of this, that's 4 minus lambda into 3 minus lambda minus 1 times 2, that's 2. All of that equals 0. So if you expand this now, 4 minus lambda times this, 4 times 3 is 12. 4 times minus lambda is minus 4 lambda. Minus lambda times 3 is minus 3 lambda. Then plus minus lambda times lambda, that's minus lambda squared minus 2. All of this equals 0. So that you have lambda squared minus 7 lambda, then 12 minus 2. 12 minus 2 is actually 10. And all of this is equal to 0. All of that is 0. So if you factorize this, you just get lambda minus 5 into lambda minus 2 equals 0. So that means lambda is either 5 or 2. So that's why the lambda 1 and lambda 2 are what you have like that. So lambda 1 is 5 and lambda 2 is 2. So, of course, the transpose of the matrix now is 4, 1, 2, 3. So, interestingly, you discuss now. Maybe, okay. Before I even take that away, it is very important to see something here. I think I'm going to do a video to talk about how you can get the characteristic equations of square matrices. So, if you look at this now, you will discover that this is the characteristic polynomial right here. The characteristic polynomial of this equation, of this matrix, is lambda squared minus 7 lambda minus 10. Now you'll discover that it's the same thing as lambda squared minus the trace of the matrix. That's the addition of the numbers on the principal diagonal. That's 4 plus 3. That's 7. So it's more like you have the trace times lambda minus 10. If you look at 10, 10 is the determinant. 4 times 3, 12. 4 times 3, 12 minus 2, that's 10. So you have lambda squared minus trace lambda, then minus, or rather plus the determinant equals 0. So that's the interesting thing you see here. So it means that if you're going to write the determinant of this one too, so you have lambda squared, the trace is 4 plus 3 also, which is 7 lambda, and the determinant is 4 times 3, 12. 12 minus 10. 12 minus 2 is 10. So you have minus 10 again, and that is 0. And since if they have the same determinant, they automatically have, oh, sorry, this is plus 10, sorry. So this is plus 10. So since they have the same characteristic polynomial, they will definitely have the same eigenvalues, because if you solve this again, you get the same lambda minus 5 into lambda minus 2. So that lambdas will be 5 and 2. So you see that it's very true that the transpose of a matrix has the same eigenvalues as the original matrix. Okay, so that's the first property. So if you know if I told you the determinant of a particular, the eigenvalues rather of a particular matrix, then you don't need to look for the eigenvalues of its transpose, because the eigenvalues are exactly the same, for the two matrices, the original matrix and its transpose. Very important. Okay. So the second property is about trace. So the trace of a matrix, of a square matrix, is the sum of its eigenvalues. So the sum of its eigenvalues. So we are using the same metric. Consider the matrix A, 4, 1, 2, 3. Its eigenvalues are lambda equals 5 and lambda equals to the one we just found. Then you discover that the trace of A is the addition of the elements on the principal diagonal. That's 4 plus 3, which is 7. Now you see it's the same thing as lambda 1 plus lambda 2, which is 5 plus 2. And the answer is 7. So you see that the trace of a square matrix is equal to the sum of its eigenvalues. Very important. Very important. Okay. So if I tell you that, if I give you a particular matrix and I tell you to find the determinant, and I tell you to find the trace of the matrix. If I give you the eigenvalues of a square matrix and I tell you to find the trace, you don't actually, of course, trace is easy, right? You can easily add this up. So after adding 4 plus 3, that's 7. You want to check if it is correct by adding up the determinants also. The eigenvalues also. So they have to be the same. So 4 plus 3 equals 5 plus 2, and that is 7. So that's very important. It looks very simple, but you'll see how important it becomes when you have maybe very large matrices to deal with. Okay, so let's talk about the determinants. Like I've hinted you ahead, generally speaking, for a 2 by 2 matrix, you can just write the characteristic polynomial by saying lambda squared minus 5, minus the trace, let me just use TR for trace, times lambda, minus the determinant equals 0. That's general stuff. So I'm going to make a video, I think, for that, to explain that for 2 by 2 and 3 by 3. Okay, so here you discover that the determinant of a square matrix is the product of its eigenvalues. So if for you to know that you have got the right eigenvalues, by the time you multiply your eigenvalues together, you should get the determinant of the matrix. So consider the matrix A, which is 4, 1, 2, 3 as usual. So its eigenvalues are lambda 1 equals 5 and lambda 2 equals 2, which we found not quite long. So the determinant of A is 4 times 3 minus 2 times 1, 4 times 3 minus 2 times 1. That's 12 minus 2, and that is equal to 10. Okay, that's the determinant of this matrix, right? That's the determinant of this matrix, 10. And this is equal to the product of its eigenvalues. What are the eigenvalues? You have lambda 1 times lambda 2, and that is 5 times 2, which is equal to 10 also. So you see, the determinant is 10, and the product of the eigenvalues is also 10. So generally speaking, the determinant of a square matrix is the product of its eigenvalues. Very important. Very important. Very simple, but yet powerful, especially if you are dealing with so large matrices. Okay, the next thing is about scalar multiplication. So given a square matrix A and a scalar K, the eigenvalues of Ka are are K times the eigenvalues of A. Now, what we are simply saying here is this. You have your matrix A, right? A has its eigenvalues. But if you multiply that matrix A by a particular scalar value, K, so the eigenvalues of the product, the scalar product multiplication and the scalar product is going to be that value K multiplied by each of the original eigenvalues of matrix A. For instance, now, consider the matrix A, which is 4, 1, 2, 3, the same one, with eigenvalues lambda 1 is 5 and lambda 2 is 2. So now let K be 5. If you take a scalar value 5, so that means that Ka, which is 5A now, will be 5 times 4, 20, 5 times 1, 5, 5 times 2, 10, 5 times 3, 15, like that. So we have that matrix 5A. So you discover that the eigenvalues of this, like we've said, of course, normally, if you are going to look for the eigenvalues, we just say 20, 20 minus lambda multiplied by 15 minus lambda minus 50, okay, equals 0. So if we solve all that, at the end of the day, you end up getting lambda to be 25 and 10, all right? 25 and 10. And that is exactly what we have. So based on this rule now, the eigenvalues of this will simply be the first eigenvalue. So if you call this lambda 1, 1, so to speak, so it should just be 5 times the original lambda 1. You have 25. Or instead of just calling this lambda 1, 1, I think normally let's just that this eigenvalue is going to be 5 times lambda 1, which is 5 times 5, and the answer is 25. The other one is going to be 5 times lambda 2, that is 5 times 2, and it is 10. So if you solve this one also, you get the same 25 and 10. So given a square matrix A and a scalar K, the eigenvalues of K are K times the eigenvalues of A. So any number you multiply the matrix with, the eigen so the same number will be is what will you multiply the eigenvalues of the original matrix A with to get the eigenvalues of the new matrix. All right, so very interesting properties right here. Okay, let's go for the next one. Matrix power. Matrix power. Given a square matrix A and a positive integer K, the eigenvalues of A raised to power K are the eigenvalues of A raised to the power of K. So for instance, again, you have that matrix A, the same matrix we've been working with. Consider matrix A, which is 4, 1, 2, 3, with eigenvalues lambda 1 equals 5 and lambda 2 is 5. Now let K be 3. So if we say A raised to power 3, so if you raise this matrix to power 3, this is what you get: 86, 39, 78, 47. So if you do the normal process, and you get, say 86 minus lambda into 47 minus lambda minus 78 times 13, and that's like a big number, right? And all of this equals 0. If you solve it at the end of the day, you're going to get your lambda to be 125 and 8. But then instead of going through that stress, since you know the matrix it's coming from, the matrix is A, and the power to which it is read, that is 3. So just raise each of the eigenvalues, to the power of 3, and then you get the eigenvalues of the new matrix. So the eigenvalues of A cube will just be lambda 1 raised to power 3, which is 5 raised to power 3, and that is 125. And of course, lambda 2 raised to power 3, which is 2 raised to power 3, which is 8. And how do you know if you are correct? You already know that if you add your eigenvalues together, you should get the trace. So you say 125 plus 8, that is, that's lambda 1 plus lambda 2, that is 125 plus 8, and that is 133. Now check that if you add 86 and 47, do you get the same thing? 86 and 47, that's 3, 3. So that's 133. So the trace is correct. So if you also multiply the two, 125 times 8, you get 1000. All right. So if you do 86 times 47 minus 78 times 39, you're also going to get the same 1000. So that way, so even with the trace alone, you can even make your conclusion that the answer is actually correct. Okay. So that also works. So if you raise the matrix to a power, the determinant of the new matrix is going to be the determinant of the original matrix raised to the power to which you raise the matrix. All right, so that's really another interesting property. Okay, so we have also something about the inverse. So the eigenvalues of the inverse of a square matrix are the reciprocals of the eigenvalues of the original matrix. So if you have the matrix A now, this matrix A, which is 4, 1, 2, 3 as usual, with eigenvalues lambda 1 equals 5 and lambda 2 equals 2. So the inverse of A, which is A inverse, of course, the inverse of this matrix is 1 over 10 into 3 minus 1 minus 2, 4. We already, I have previous videos on how to find inverse, so you can refer to that. So the eigenvalues of A inverse will simply be the reciprocal of the original of the lambda 1 and lambda 2. So here we have 1 over lambda 1, which is 1 over 5, and 1 over lambda 2, which is 1 over 2. Again, how do you know if you're correct? The numbers along the principal diagonal here will be 3 over 10 and 4 over 10. So if you add 3 over 10 plus 4 over 10, you get 7 over 10 straight up. So confirm by adding these two lambdas now, these two values. So you have 1 over 5 plus 1 over 2. So LCM again is 10. 5 and 10 is 2. 2 times 1, 2. Plus 2 in 5. 2 in 10, 5. 5 times 1, 5. And that is also 7 over 10. So that means that these values are correct. All right. So these are interesting rules to go by, interesting properties of eigenvalues. Okay. All right. So in conclusion, we see that eigenvalues possess several important properties that are useful. They are very useful in various areas of mathematics, including linear algebra and differential equations. Now, we have not seen those applications about differential equations, but maybe in the future, when I get to talk about differential equations, you'll understand. Then understanding the properties of eigenvalues allows for deeper insights into the behavior of linear transformations and systems of equations. Very important. Okay, so we have some practice questions which will really be helpful to train your hands. So see these questions now. So try your hands on these questions like I always like you to do. The eigenvalues of the matrix P, which is 5, 4, 3, 1, are 7 and minus 1. So I've given you the eigenvalues. Find the eigenvalues of P transpose 11P, P cube, and P raised to power minus 1. Now, normally, for people that do not, for those who do not still understand what I did, they will still now they will find the transpose of this and start looking for the eigenvalues, or they multiply 11 by P and start looking for the eigenvalues, or they will raise P to power 3 and start looking for eigenvalues, or find the inverse and look for eigenvalues. But no, it's not necessary because I've given you the rules. First of all, you know that for P raised power P transpose now, the eigenvalues are going to be the same as the eigenvalues of the original P. So the eigenvalues of P transpose will be 7 and minus 1. So for P transpose, you have 7 and minus 1. Now for 11P, you already know it's going to be 11 times 7. That will be 77 and minus 11. Okay. For P raised to power 3, whatever P raised to power 3 is, yeah, the eigenvalues are going to be 7 raised to power 3. 7 raised to power 3 is 7 times 7, 49 times 3. I think that should be 147 or something. I'm not very sure. I think so. And then the other one is minus 1 raised to power 3, which is simply minus 1. All right. Then finally, P inverse. P inverse, you know that you should know that should be 1 over 7 and minus 1. That's 1 over minus 1. So you don't have to start getting these matrices and look for the eigenvalues, because you know the rules already. Just follow the rules and you'll be fine. So the same thing is what you're going to have for the second question. The eigenvalues of the matrix Q, which is equal to 5, 2, 2, 2, 5, 2, 2, 2, 5, are 9, 3, and 3. Find the eigenvalues of Q transpose, 7Q, Q cube, Q inverse. Again, you don't have to look for Q transpose. Just say for Q transpose, the eigenvalues are going to be the same. For 7Q, the eigenvalues are going to be each of these multiplied by 7. For Q cube, the eigenvalue of these ones are going to be each of them raised to power 3. And for the inverse, the eigenvalues are just going to be the reciprocals of the ones you have been given already. So it's so interesting, so sweet. So try your hands on this and see what you get. Okay. Of course, I mean, you may want to satisfy your conscience to go through the normal process to confirm that these rules actually work. So if you have not subscribed to my channel, please do that so you do not miss these juicy videos that will keep coming your ways. Thanks for listening. See you in the next video.